Welcome back! In the previous video, actually in a video I published 14 months ago, I showed you how to unlock all 4 hardware serial ports of an Arduino Nano Every. Card here, link in the description. In this video I want to talk about the megaAVR MCU's Watchdog timer and reset controller, again using the Arduino Nano Every as an example. Enjoy! Let's talk first about the megaAVR 0 series reset controller. And yeah, the ATmega4809 inside your Nano Every is a megaAVR 0 series MCU. Here's the block diagram of the whole thing. So no surprises here on the hardware side. We have our reset pin, we know that, with a pull-up resistor to VDD. But then we have that block here with a whole lot of reset sources. We have a power on reset. We have a brown out detection, where if VDD falls too low. We have an external reset, of course, which we can initialize via pulling the reset pin low. We have a Watchdog timer reset. Yeah, we will talk about that a bit later. Then we have an UPDI reset. That's the Universal Programming and Debugging Interface. We'll talk about that in a second. And then you have a software reset via the CPU, and that goes into a reset controller and resets all the stuff in your MCU. The reset controller is controlled by 2 registers. First, we have here the RSTFR, or reset function register, which provides you 6 flags here that indicate what kind of reset happened actually. And then we have the software reset register, where you write simply a 1 in that last bit here to cause a software reset. Here we have the details of the reset flag register, RSTFR. As I mentioned, these 6 bits are just indicating what kind of reset occurred. So UDPI, software, Watchdog, external, brownout, or power on. Please note, these flags do not reset by themselves. If a reset occurred, they stay 1. You have to manually reset them to 0 by writing a 1 to them. There's an exception, of course, that's the power on reset flag. If a power on occurred, of course, all flags are 0, but for the power on reset flag. Meaning, if you have a power on reset, that is, you switched on VDD and then you have, for example, a Watchdog reset and a software reset, all these 3 flags stay set. And you have to manually reset them by writing a 1 to them. Only on a power on, the flags are cleared, and then, of course, the power on reset flag is set again because we had another power on. Let's talk about the Universal Programming and Debugging Interface, UDPI, of the ATmega4809 now. That's just a single pin, and it implements a serial interface, with the ATmega4809 being a slave in that interface, and it allows you first to program the flash memory just by sending commands over here, and to debug code executed here in your MCU. That is, you can send commands over here entering a single step instruction mode, and sucking out register and memory content over that UPDI. What you can also do is send a command over the UPDI to your ATmega4809 to reset it. And that reset, yeah, we saw it in that initial block diagram. Where is it? UDPI is one of the reset sources. And we see that reset flag also in the register. That was a UPDI reset flag. The Arduino Nano Every has a second MCU here. That's a SAMD11. That's the official writing from Amtel. There's a space here between the M and the D. And that MCU contains your classical bootloader and a piece of USB to serial software. And of course, that SAMD11 is connected to your USB port and on the other side to a serial port of your ATmega4809, and it has that UPDI connection here. So if the bootloader detects that you don't want to talk to some serial monitor or a serial plotter, but you want to program something, then the bootloader uses the UDPI to flash the memory of the ATmega4809, and then it sends a reset command over that line to your ATmega4809. And afterwards, the ATmega4809 can use serial 0 here with that USB to serial software piece to talk to your serial monitor or serial plotter or any other serial program on your PC or wherever your USB port might reside. The important thing here is that your ATmega4809 and Arduino Nano Every just executes the sketch after receiving a reset, either via UPDI or another reset source, power on for example. That's different to older Arduinos, where the bootloader also resided here in your MCU and first did all its bootloader stuff and in some cases resetted all the reset flags, preventing you from reading those reset flags in the sketch. I should mention there are other bootloaders out there for those older Arduinos that preserve somehow the reset flags. But anyway, let's move on to the second register of our reset controller, the software reset register. There's only a single interesting bit in here, and that's the software reset bit. Just write a 1 to it and you cause your megaAVR to perform a software reset. But this bit or this register is configuration change protected. Meaning you have to write a certain key to the CPU configuration change protection CCP register before you can write the software reset register. Let's have a look at some code utilizing that reset controller. So first of all, you need to include the avr/io.h file. That will define all the registers and bits and stuff you need to handle all AVR registers, not only the megaAVR registers. More on that later. For now, you can ignore that avr/wdt.h. We will need that for the Watchdog timer later on. In the setup, I first open the serial port on my USB so we can print something, and then I print that I entered the setup. Then I call a function print reset flag registers, then I clear the reset flag register, and then I print it again. Finally, I print exiting setup at the end of the setup. And we will have a look at those functions in a second. In the loop, I just print out that I entered the loop and at the end that I exited the loop, and in between I wait for a second and then I call the function software reset. And now let's have a look at all these functions. The print reset flag register function starts with a very long command where I documented everything you ever need to know about that reset controller reset flag register. And these macros here and stuff are all defined in io.h, which in turn includes for the ATmega4809 IOM4809.h, and that is controlled by the macro AVR ATmega4809 being defined before you include io.h. The Arduino environment does that for you. And then io.h, respectively IOM4809.h, also defines AVR IOXXXH as IOM4809.h, so the actual include file we are using for that MCU, and it also defines that AVR ATmega4809H included macro. And I have, you cannot probably read that completely, but here I have the path where, at least in a Windows installation of Arduino, you can find all these files. Anyway, both registers of the reset controller are defined in a struct, and the first member of that struct here is our actual reset flag register, that single byte here. And then we have the bit masks for all the 6 bits defined, so for power on reset, brownout, external, watchdog, software reset, and the UDPI. We also have defined, if you need it for bit banging, the positions of the flags in the same manner. So that's these values here are between 0 and 5. The function itself then prints out a nice header with tabs in between, and then first the complete contents of our reset flag register, and then it does some bit banging and compares each and every of our six flag bits and prints out true or false depending on the value of the bit. Clear reset flag register just writes once, so everything odd here, all our 6 bits here to the reset flag register to clear each and every bit. Finally, we have the software reset function that starts exactly the same with lots of commands, and first defining all the include stuff, how that works. We already seen that. It works exactly the same, but this time we are using the software reset register member of the reset controller struct. And we have only 1 bit defined here, the software reset bitmap, so the bit mask, and the software reset bit position, which is 0. We also use the CPU change protection in this function. The include, again, is exactly the same mechanism, and it defines a CPU underscore CPP register you can write. That's the CPU change protection, and it defines 2 keys in an enum. And that would be the CPP SPM-GC, that's the SPM instruction protection. We don't care about that, but we care about the CPP IO rack. That's the IO register protection, and that includes our reset controller software reset register. And then the function simply writes to the CPU CPP register the appropriate key to unlock our software reset register, and then we write the software reset bit to that register, and we should have a software reset. And here's our output on the serial monitor. And I just let it run for a little bit, and then I'm pulling the plug and we can go over it. So we first enter the setup and we print out the content of our reset flag register, and we can see here, yeah, it's 10000, that the UPDI reset flag is set, meaning the bootloader in the SAMD11 resetted our ATmega and to execute our sketch. Then remember, I clear the registers, so the next time I print them out, it's all 0. We are exiting the setup then, and we are entering the loop where we do a delay of 1000 milliseconds, 1 second, and then we do our software reset. So we never exit the loop. Instead, we are entering again the setup. And this time, if we read our reset flag register, we see that the software reset flag has been set. And yeah, we clear the register and all flags are 0 again, and so on and so on and so on. Now, what happens if I don't clear the reset flag register and I also don't need a second print here? I'll upload that and then we have a look at the serial monitor again. So, and on the serial monitor, things look a little bit different now. Let me just pull the plug and scroll up and we can go over it. So I'm not clearing the reset register, and you can see that both flags survive each and every of our software resets. Only a power on would clear all these flags, but for the power on reset flag, let me put that code back in. And no, I don't want to update right now. But we haven't seen the power on reset flag, and that's because setup is not the first code that is executed in a script. Before that, the main function, which is within the Arduino environment, is called, and that calls several init functions, which obviously clear the power on reset flag. So you never get to see it, which is a bit unfortunate, but it is what it is. Let's talk about the Watchdog timer now. In its simplest form, it's just a counter that continuously counts up until it reaches a certain value here called period. And in that case, the system gets a reset, a Watchdog reset, unless you reset the counter back to 0 before that set period is reached. The Watchdog timer is controlled by two registers, the Control A and status register of the Watchdog timer. We won't go into all the details about the registers because within the Arduino environment there is a little library providing you functions to make the Watchdog timer work. So we won't have to write directly to these registers. The Control A register contains two groups of 4 bits here. First, the period of our Watchdog timer and then the window. We will talk about the window later. Please note that this register is also configuration change protected, like that one register of the reset controller. But the library will take care of that. Into that 4-bit period, we can write different values ranging from off, self-explanatory, Watchdog timer does nothing, and then starting from 8 cycles, that's from a 1 kilohertz clock, so 0.08 seconds, up to 8.2 seconds. To be exact, 8.192 seconds, because these K here for clock are binary Ks. So 8K is 8 times 1024. Let's have a look at the code then. We still need the AVR IO.h because all the bits we need to set in the register are defined in there. But we also need now the Watchdog timer.h, which will define two functions we are using to program and reset the Watchdog timer. Please note, io.h and the subsequently included files are obviously provided by AVR for its microcontrollers, while Watchdog timer.h is a part of the Arduino environment. In the setup, I just uncommented that line set watchdog timer, which gets two attributes. First, the watchdog period, in this case 1 kiloclock, so 1024 milliseconds, and the window, we talk about that later as I mentioned, which is currently off. In the loop I decreased the delay here to 900 milliseconds and I commented out our software reset. Instead I'm now doing a reset watchdog timer. My function setWatchdogTimer gets two arguments as we've seen. First, a VDT watchdog timer period enum period and a window enum window. Both enums are defined via the io.h, exactly the same mechanism we've already seen. I've mentioned before that the timings are all based on a 1 kilohertz clock, but that clock is not derived from your usual 20 megahertz clock, but instead from a 32 kilohertz ultra low power oscillator, which also keeps running while your megaAVR is in sleep mode, just if you wanna tinker around with that. Anyway, we have that watchdog period type def enum here in that file, which is also available as watchdog timer period t. And there we saw that already in the datasheet. We have different definitions, members from off, so watchdog timer off. And then starting from 8 clock cycles to 8 milliseconds up to 8 kiloclock cycles, so 8192 milliseconds. Finally, I call the function watchdog timer enable that is actually defined in that watchdog timer enable.h file. The file is a little bit messy. I provide the path here, so have a look at it if you want. Just note that file also defines for the megaAVRs a function watchdog timer disable. That's not the correct function for the megaAVRs. Instead, please use the watchdog timer enabled with watchdog timer period enum set to watchdog timer period off. That leaves us with the reset watchdog timer function, which does nothing else than calling the watchdog timer reset, also defined in that watchdog timer.h. Let's find out how the whole thing looks on the serial monitor. And it looks boring. I mean, we have here our UPDI reset, okay, from the bootloader, and then we enter the loop and exit the loop and enter the loop and exit the loop and so on. But guess what happens if I comment out the reset watchdog timer in the loop? Let's have a look at the serial monitor again, and things look different. Let me pull the plug and let's go over it. So we start normally with an entered setup and the UPDI reset flag is set, and we clear all our reset flags. Then we exit the setup and we enter the loop, and we exit the loop and we enter the loop again, and then we are back in the setup. we experienced a Watchdog timer reset. And we can see that in the reset flag register, because now not the UPDI reset flag is set, but the Watchdog reset flag is set. So we know when we enter the setup that our Watchdog resetted the whole thing, because we forgot to reset the Watchdog timer. That can be used, of course, to reset your whole thing when your code hangs in some way, runs in timeouts or whatnot. So it's quite useful, and it's also quite useful to be able to decide if we have a regular startup via the bootloader, the UPDI interface, or if our Watchdog reared its ugly head, meaning something is wrong with our code or our attached hardware or whatever. Now, let's talk finally about the window stuff, or the window mode operation. We have a second 4-bit field, which also defines a window between 8 milliseconds and roughly 8 seconds. And in that window, after a reset of the Watchdog timer, you are not allowed to reset the Watchdog. Only when that period is over, the normal Watchdog timer period starts, and then within that period you can reset you have to reset the Watchdog if you want to avoid the Watchdog resetting your chip. Please note, these two intervals which we can define are additive, and they add up to roughly a maximum of 16 seconds. We are back in the Control A register of our Watchdog timer, and we are now looking at these 4 window bits. And as you can see, they range like the period bits from off, so window function is off, and then starting with 8 clocks, so 8 milliseconds, up to 8 kilo binary, so 8 times 1024 clock cycles. And here they put in the exact numbers, so 8.192 seconds. In my setup, I'm no longer providing here window enum, window off, but instead a window of 512 clock cycles or 512 milliseconds. In the loop, I just reactivated our reset Watchdog timer. And now we can talk about the window enum window argument here to our set Watchdog timer. That enum is also defined in io.h. We've seen that often enough. And it provides the same values we've already seen in the datasheet. So off, and then from 8 milliseconds up to 8192 milliseconds. And my VDT enable gets the period, so that one 4-bit group binary odd with the window, the other 4 bits in that register. So let's have a look at the serial monitor, and we see nothing. So our UPDI reset, and then just entering and exiting the loop as expected. But what if we now put our reset Watchdog timer before the delay? Let's have a look at the serial monitor. And, well, still resetting the Watchdog, which is odd. Because I would have expected, since we set the Watchdog timer here for the first time, that immediately resetting the Watchdog timer would actually result in a missed reset, because our reset falls into the 512 millisecond window. However, after that 512 millisecond window, so when we resetted the Watchdog timer and missed the window, so to say, we wait another 900 milliseconds and then we reset the Watchdog timer. So we are well within the period window which comes after the window where we can't reset. So another about 1000 milliseconds. So this does absolutely nothing. Let's do a more complicated timing then. I first do a delay of 400 milliseconds. So we should be within that forbidden window of 512 milliseconds for our first reset Watchdog timer. And that should be ignored by the Watchdog timer. And then I do a delay of 1300 milliseconds, bringing us to a total of 1700 milliseconds, which should be outside the 1024 plus 512 milliseconds here. And then I do another reset Watchdog timer, which should be too late. Let's have a look at the serial monitor then. And that's odd. So we have our UPDI reset here. So the first time we are entering setup, and then we exit setup, and then we enter the loop and do our odd timings, but we are still exiting the loop without a reset. Then we enter the loop again, and then a reset occurs because we are back in the setup with the Watchdog reset flag set. What's that all about? That's about reading each and every sentence in a datasheet, of course. And under Windows mode, we find that here. When enabling window mode or when going out of debug mode, the first closed period is activated after the first reset instruction. Yeah. And now we understand what's going on here. So we enable here our window, and the first reset Watchdog timer is actually resetting the Watchdog timer because, as we've learned, the window function is only enabled after the first reset. Then we do a 1300 millisecond delay, which is completely within the window. So we reset the Watchdog timer a second time. And as we re-enter the loop, the window is now, of course, activated. So after another delay of 400, the second first in the loop reset Watchdog timer is ignored because it falls into our 512 millisecond window. And so adding up now the 400 and 1300 milliseconds, 1700 milliseconds, our next reset Watchdog timer comes too late. And so the Watchdog timer resets our chip. Before we finish this video, a little note about hardware reset. I mean, we have this nice button here, and if I press it, I can do a hardware reset. And yeah, we see that hardware reset. Let me stop the auto scroll here and go back, or yeah, I pull the plug and go back a little bit, and we see that the external reset flag is set. So to summarize, we can, on an Arduino Nano Every with a megaAVR processor, distinguish between the UPDI reset, then a software reset, a Watchdog reset, and an external reset. So a low signal on the reset pin of our megaAVR. Please note that you probably won't ever see a power on reset, because that's handled by the SAMD11. What you might see, and I cannot test this, at least not with just the rare board, is a brownout reset, because the SAMD11 runs on 3.3 volts. So if your input voltage, I don't know exactly what the brownout limit is for megaAVR, but if the brownout voltage is, let's say, 4 volts, your SAMD11 might still be happy, but yeah, your megaAVR 5 volt version might experience a brownout. That's it for today. I hope I wasn't too incoherent towards the end, because I'm experiencing here currently 34 degrees Celsius, so it's getting a little bit hot in here. But anyway, I hope you enjoyed it, and till next time, bye.